Hi, Calculus. We're on our 5th unit, curve sketching, which is the unit I said you'd use some of your functions understanding from last semester. We're going to be creating a toolbox of things that you can use to help you graph quickly and efficiently using calculus methods. Some of it's going to be very intuitive, so I'm not trying to insult you today, but we're going to look at increasing and decreasing functions. So we say that a function is decreasing if your y values are going down. We say that a function is increasing if your y values are going up. So we're going to be looking at y equals x squared to get ourselves started. So let's look at a function and its derivative, and we'll look at the graphs in a moment. So if we have y equals x squared, my y values would be 9, 4, 1, 0, 1, 4, 9. My derivative, which is 2x, would have values of -6, -4, -2, 0, +2, 4, and 6. If we look at the graph of the function, I have a quadratic, and I have an uncentered graph. Okay, see if this is any better. Little. Okay. 2, 4, 3, 9. Okay, here is y equals x squared such that is oh, lumpy smartboard, lumpy smartboard. There we go. Sort of y equals x squared. The derivative values that we just created, we have values of +2, +4, and so on. -2, 4. Okay. We can see by the graph that my y values are decreasing here and increasing here. I can see at the same time that my derivative values are negative here and positive here. So I have an increasing function as it turns about 0. Increasing, 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 and I have just this momentary pause at 0. I notice on the left side of the graph as we come towards 0, it's decreasing, decreasing, decreasing. Okay, let's try a new function, and we're going to be looking at the critical points, those places where we change from increasing to decreasing. So we're going to use the derivative to tell us those intervals. Intervals. So our derivative, sorry, this thing just got wrenched off of my head. The derivative is 3x squared subtract 8x plus 1. So right now on this graph, I'm just going to be looking at the derivative. So in order to get a sense of it, I'm going to set it equal to 0 so I know where the derivative's x-intercepts are so that I can graph it. So if I have 3x squared subtract 8x plus 1, I would try my darndest to factor it, and oops, it's not very nice. So to find those x-intercepts, I'm going to use the quadratic formula, +8, add or subtract the square root of b squared minus 4ac all over 2a. I end up with two possible roots of 2.6 or approximately decimal 1.3. So just really not accurately. 2.6 approximately right there. So I have a quadratic with a positive leading coefficient. I know more or less my curve will look like that. And these are the important places where my derivative function goes from positive to negative to positive again. Those are critical points, very important. We could certainly calculate the vertex of this function. I wonder if it tells us anything important. At this point, we're going to create a nice, neat table and just look at intervals of increase and decrease. So I know that those important values for x are 0.13 and 2.6. And I'm going to ask you to set your table up nice and neat and tidy so we can all be on the same page. So I know that my derivative is 0 at those two places. So those would be my critical points. That's going to tell us something about the function itself. So I want to look in the intervals to the left of 0.13. I want to look in the interval between 0.13 and 2.6. At 2.6, we already talked about that, and to the right of 2.6. So if I have a value of less than 0.13, I am substituting that value into the derivative function. And I could use a calculator, I could do it in my head if I wish, but all I want to know is the sign of the resultant. And if I put that into the derivative function, I get a positive value. I'm going to choose a value between 0.13 and 2.6. I'm going to use x equals 1. You can use whatever you want in there as long as it falls in that interval. So I would have 3 times 1 squared is 3, subtract 8 times 1 is 8, so I'm at -5 plus 1, -4. So my value is negative. That's all I care about. I want a value larger than 2.6. I put it into my derivative function. This is where you're trusting me with my calculator. I'm choosing a value of 3. So I have 3 times 9, 27, subtract 24 is positive 3, plus 1 is 4. So I get a positive. That tells me that I have increasing in my original function. This is a turning point. Change direction, and then we decrease. Then I turn again. And then I'm increasing. So if we are changing from increasing to decreasing, I have a maximum here. If I go from decreasing to increasing, I have a minimum value here. I should have a few points that could be helpful before I graph this thing. So this can help me with some really key points. Then I want some specifics for my graph. I want to know the value of the function at that really important point. Let's find the value of the function at 2.6 as well, since it's so important. I'd like a value of the function in each one of those intervals. So I looked at 1, -1. Let's look at 3. So those should get us anchored, and then my little chart can help me graph it actually. So 0.13 into the original function, I get 1.06. 2.6, approximately, sorry. 2.6 into the original function is -5.84. -1 is -5. 1 is -1, and at 3, it's -5. So these can be helpful points. And we're going to draw a rough sketch based on the information that we have. I'm going to start with those key values. At 0.13, I have 1.06, so excuse my inaccuracy, but here we are. I know that that is going to be a maximum. At 2.6, I have -5.84. And I know that is going to be a minimum. At -1, it's -5, 2, 3. At 1, it's -1. At 3, 1, 2, 3, 4, 5. Okay. So from my critical points, that table that I organized, I know that this one is a maximum. I know the 2.6 is a minimum. I know it's a cubic, so I know the basic shape. And very roughly, yeah, you can do a better job. I have that. And crazily enough, in this unit, you can always check your work on Desmos. Let's look at a last example. F at x equals x ln x. So we know that the derivative function can help us find critical points. So let's find the derivative. So the derivative of this product would be derivative of the first times the second plus the first derivative of the second. Awesome. We have ln x plus 1. To find critical points or turning points, these are critical, not as in you don't look nice today, just saying. We want to know where the derivative is 0. So I'm going to set my derivative function to 0. I'm going to subtract 1 from both sides and go, oh no, how do I deal with ln x? We e both sides. If we can make a verb of that. If you e ln x, well, let's write it. E ln x, I have x. E to the negative 1 is 0.36 approximately. Okay. So I'm going to set up a nice little chart to organize my thinking. This is a nice simple chart because there is only one critical point. I want to look at 0.36, to the left of 0.36, and to the right of 0.36. Okay. At 0.36, the derivative is 0. So that tells me the function has a turning point there. To the left of 0.36, I am looking at the derivative ln x plus 1. So ln of something less than 0.36 would be negative. So we're picturing ln x plus 1. So ln x would look like this. Ln x plus 1 would be 1 up. So it looks like that. If we have a value less than 0.36, we have something that's in the negative. If we have something greater than 0.36, we have something that's positive. That tells us my function is decreasing, and then it's increasing. So we know that this turning point is a minimum if we are decreasing and then increasing. I'm just trying to show direction here. All right. Okay. Let's just come up with a couple values that can help us get anchored before we try and graph it. So we know just some interesting things. We know that our function has no y-intercept. That can be such a helpful point to anchor ourselves on a graph, but it doesn't exist. We would love to find x-intercepts, so that's when our function itself is 0. These can be really nice key points. So let's see if we can find that. Otherwise, we'll just look at this turning point. When is our function 0? Well, our function is 0 when x is 0. That's not possible because you can't have ln of 0. So we can't have an x value of 0. It has to fall in this domain. Or when is ln x 0? That is true when x is 1. If we could e both sides, we would have a value of x equals 1. So I have an x-intercept of x equals 1. Let's put that on our graph. All right then. Let's find a specific value for our critical point. Okay. I have negative 0.368. Let's include a point to the right and a point to the left. So if I look at the function at point 2, and if I look at the function at 2, I could do it at 1, doesn't matter. I have values of -0.32 and +1.4. Let's put those values in. So 0.36 is our minimum. Our other two values at 2, 1.4, the other one, it's hard to see. I should have increased my scale. 0.2 is -0.32. There. We know that x has to be greater than 0, so we've got a hole there. That's supposed to be a hole. Let's try it again. And so our curve would go down to the minimum with a turning point at 0.36.